Hey everyone, my name is Sebastian,
My name is Pedro.
My name is Quentin.
My name is John.
and today we're going to be talking about the high temperature water gas shift reaction. So let's get started.
So, for some background, hydrogen is the most abundant chemical substance in the universe, yet it is relatively difficult to obtain. Hydrogen has many different uses, especially in various environmental applications. Hydrogen is considered an ideal fuel due to its ability to produce zero emissions when its energy is harnessed. As we see the devastating effects of climate change, in addition to the diminishing amounts of fossil fuels, it is with great urgency for us to devote our time and effort into something that combats this. We are going to discuss means of obtaining hydrogen via a high temperature water gas shift reaction.
The kinetics of the WGS or water gas shift. So it's a slightly exothermic equilibrium based gas phase reaction. You can see there CO plus H2O yields CO2 plus H2. This reversible reaction is exothermic and consequently its equilibrium constant, K equilibrium, decreases with temperature. This means that as temperature increases, the product yield will fall. If the reaction is ran at a low temperature, the kinetics are very slow, and if the reaction temperature is too high, the equilibrium constant will be very small, so there is a silver lining for the reaction to proceed favorably.
So, discussing the catalyst we'll be using, the details and specifics won't be covered here, but in this case, an iron chrome commercial catalyst will be used called high fuel W210. This catalyst is 88 weight percent iron oxide, 12 weight percent chromium oxide, and 2.5 weight percent copper oxide. This is an ideal catalyst for high temperature water gas shift reactions.
So for the rate law, you can see right there, RA equals K times partial pressure of A times partial pressure of B minus PC over PC, species C and D, over K equilibrium. So the rate law of this reaction is best modeled in terms of partial pressures, a common practice when there's a catalyst involved, like this one, where Pi are the partial pressures of our species and Ka and K equilibrium are the rate constants. The goal of the catalyst is to lower the activation energy E so the reaction can proceed using a lower energy pathway. And you see how E affects the rate constant there. So yeah, in the Arrhenius equation.
All right, for undesired reactions in our water gas shift, there's one governing term that'll control the conversion and rates of any undesired reactions. This is the ratio of our H2O to CO. If this ratio is low, so there's less than 1 mole of H2O per mole CO, there will be several undesired reactions taking place in series and parallel. However, if this ratio is kept high, the side reaction conversion rates and kinetics can comfortably be considered negligible. Here are some of the side reactions that can be considered, in which the very first one you see is 2CO goes to a solid carbon plus CO2.
So for our reactor, to make use of our catalyst effectively, a PBR, packed bed reactor, would model our system most accurately. We can apply our CRE algorithm to produce the following design equations. So we start on the far left with the mole balance on the PBR in conversions. So dx over dw equals the rate of consumption of A over FA naught, which is the feed. So the rate law we discussed earlier and the partial pressures can be written in terms of concentration and conversion with temperature and pressure drop involved. You can see those for each species, A, B, and C, and A, B, C, and D. For a pressure drop term, we have alpha over 2P times T over T naught, where alpha is the reliant on the specifications and measurements of the packed bed. And to relate our temperature with catalyst weight, we have an energy balance on the packed bed reactor with RA, which is the rate, times the heat of reaction over the sum of Fi Cpi. And we have an equation to explicitly calculate temperature based on conversion.
All right, for the safety and assumptions of our water gas shift, we have elevated temperatures. This could lead to permeation of hydrocarbons and subsequent buildup of hydrocarbon gases in the outer membrane, which could have explosive consequences if there are impurities in the feed stream. Storage failures from the side products could lead to buildup of toxins in the environment, not so good for our workers. And so we have some assumptions to ease the process of modeling this reaction. We're going to assume it's steady state, it's adiabatic, the heat capacities of species remained constant within the temperature limits of the operation, and a PBR model was used for a reactor.
Our modeling shows these graphs showing conversion versus weight of catalyst, concentration versus weight of catalyst, temperature versus weight of catalyst, equilibrium conversion versus weight of catalyst, and pressure drop versus weight of catalyst. Each of the properties were graphed as weight of catalyst increased from 0 grams to 10 grams. The temperature in the reactor increases, catalyst weight increased, converging to about 790 Kelvin when the catalyst weight reaches 4 grams. There was little to no change in pressure in our PBR. This was mostly due to the small size of the reactor, reducing frictional losses. Moreover, the number of moles does not change as the reaction proceeds. The equilibrium conversion starts at about 91.9% for no catalyst in the reactor and starts to converge at a conversion of 90.8% at 4 grams of catalyst.
All right, the sources of error that could result from this water gas shift reaction was based off our assumptions, the errors could really arise. For this case, if we have constant heat capacities for each species, they may be an inaccurate assumption since our reactor increases in temperature to a significant amount, and it's thermodynamically proven that heat capacities are heavily reliant on temperature. One of the most direct ways that error could have affected our calculations are inaccuracies within the specified parameters. We neglected side reactions, which you will have to consider in industry, and we estimated some parameters that we couldn't find from research.
So wrapping it all up, the results of this MATLAB simulated process were found to reliably yield a 78% conversion with a catalyst weight of 4 grams. The reaction has few side reactions that can easily be selected against it by monitoring temperature and feed ratios. This process works best for recycling the waste of steam reformation processes into a safer and more useful form. Hydrogen has minimal carbon footprint effects when consumed and can be useful in the replacement of diminishing fossil fuels. The use of hydrogen gas can help lead to a society that can more effectively reuse its waste products, in addition to using more clean forms of energy. These are our references, and thank you for watching.
Have a good day.